When planning a PV system, it is crucial to know at any given time the position of the sun in the sky as seen from the location of the solar system. In today's lecture, we will introduce two coordinate systems that we will use to locate the sun in the sky. First, the geographic and then the celestial coordinate systems. There are several web applications that you can use for finding the path of the sun. For example, these pictures are obtained from Wolfram Alpha, and you can see the zenith view of the observer during the solstice of winter and summer in Delft, which represents the lowest and the highest path drawn by the sun during the year. Indeed, the maximum altitude of the sun, which will be introduced in the next slides, increases from almost 15 degrees to 61, and so also the daylight duration becomes more than the double. Note that the sun apex during the day will have a very important implication in case the PV system is embedded in a landscape with obstacles. As we shall see in the following lecture, finding the position of the sun above a solar panel situated on the Earth is not a trivial trigonometric problem. Before breaking the procedure in small steps in order to solve such problem, let's learn some important terms. To begin, we shall consider a panel as a surface tangent to the Earth crust, so it is just lying on the surface. Later on, we will tilt it in order to optimize its yield. First, we have to locate the panel with respect to the global position, and thus we use the geographic coordinate system. This system enables to specify every location on Earth with the two coordinates, latitude and the longitude. The latitude of a point is the angle between the equatorial plane, depicted in red in the picture, and the straight line that passes through that point and at the center of the Earth. Points at the same latitude trace circles on the surface of Earth called parallel. Thus, the North Pole is 90 degrees north and the South Pole is 90 degrees south, and the equator divides the globe into northern and the southern hemisphere. The longitude of a point is the angle between the Greenwich reference meridian and the meridian that passes through that point. This angle can be west or east, since the Greenwich meridians determine the proper eastern and western hemispheres. Here is shown the example of Delft, which I am now, and which is located in the northern hemisphere to east of the Greenwich meridian. This other city is Dakar, and it is always in the north hemisphere, but, unlike Delft, it is located to the west of the prime meridian. Now that we have seen the coordinates of the Earth, it will be much easier to understand the celestial coordinates. Indeed, since celestial objects like the Sun, the Moon, and the stars are very far away from the Earth, it is convenient to describe their motion projected on a sphere with arbitrary radius and concentric to the Earth. It is very important to note that because of the distance of celestial objects in general, and the Sun in particular being much larger than the radius of the Earth, we can consider the observer and the center of the Earth coincident. This sphere is called the celestial sphere, and at this point is the position of the celestial object. For photovoltaic applications, it is most convenient to use the horizontal coordinate system, where the horizon of the observer constitutes the fundamental plane. In this case, the horizon of the observer is the gray area beneath the hemisphere, and on the left-hand side you can see the representation of a plane tangent to the Earth, where the blue dot is the observer. Another important thing to realize is that your module now is the observer. Therefore, the celestial sphere will have the same inclination as this plane. As we anticipated, we may neglect the translational shift of the origin of the coordinate systems from the observer to the center of the Earth, and thus, if the PV module now it is the observer, we can always find the position of the Sun in terms of two angles. The altitude A, which is the angular elevation of the center of the solar disk above the horizontal plane, its angular range is between -90 and +90 degrees, where negative angles correspond to the sun being below the horizon and thus during night. The azimuth A, capital, is the angle between the line of sight projected on the horizontal plane and the north. It is counted eastward, such that north has an azimuth of 0 degrees, east of 90 degrees, south of 180 degrees, and finally west to 170 degrees. Its angular range is thus between 0 and 360 degrees. But note that the different conventions are also used by the PV community. For example, the south might correspond to 0 degrees and the angles might be counted westward. To be clear, from now on, we will use only the convention where A capital is equal to 0, corresponding to north. These two sets of coordinates, azimuth and the altitude of the sun with respect to the observer, is very important because they are input parameters together with the date and time to calculate the solar position in the sky. Instead of using the spherical coordinate A small and A capital, we can also use Cartesian coordinates x, y, and z. The principal direction, which is the arrow pointing north, is parallel to x, while z-axis is pointing towards the zenith. The Cartesian coordinates are connected to the spherical coordinates via this simple trigonometric relation that expresses the sun position of 3 coordinates instead of 2. So let's get things together. First, if we trace the path of the sun in the celestial sphere, we obtain the ecliptic of the sun, which is represented in orange. Then we can also draw the Earth coordinates in the same celestial sphere. So imagine to extend the equator of the Earth to the space, and thus we have the so-called celestial equator, highlighted in blue. What you find out is that the Earth and the Sun ecliptics are slanted with each other with the so-called axial tilt. This angle measures around 23 degrees, but it is not constant because it has a very little variation that depends mostly on the time. Very important is the vernal equinox, that is the principal direction of the coordinate system indicated by the sign of Aries. As it is obvious from the picture, the Aries lies in both the ecliptic and the equatorial planes, making it a reference position. As for the geographic coordinate system, here we have 2 angular coordinates called the ecliptic longitude and the ecliptic latitude. So, to summarize, today we learned how to locate an observer on the Earth's crust using the latitude and longitude of the geographical coordinate system. Then, we located the observer in the middle of the celestial coordinate system and defined the azimuth and altitude in order to describe objects in the sky, such as our sun. Indeed, the next step, as we will see in the following lecture, is to combine these 2 coordinate systems together to calculate the position of the sun in the sky.